All right, so this is it. This is the last session we're going to do for this semester when it comes to Organic Chemistry 1. We're going to do today, we're going to talk about alcohols, the reactions of alcohols, a little bit of synthesis of alcohols, and probably the most important thing that we're going to talk about today is the Grignard reaction. I think last time we left off with some nomenclature of alcohol, and since I botched that nomenclature example fairly terribly, let's just start there. Let's just warm up with just one quick example for nomenclature and try to put all that stuff back together again. So let's go ahead and switch over. And let's look at this example. I think I have it ready here. All right, so I think the example that I botched up last time involved a straight chain alkane, but here in this time we're going to use a cyclic alkane. But remember, when naming alcohols, the suffix is -al, and we still have to sort of approach it in the same way that we do other problems. Remember, the alcohol is the priority functional group. So in a straight chain alkane, you're going to number it in the direction that gets you to the alcohol the fastest. In the cyclic alkane, what that means is that the alcohol group is priority number 1. So that carbon will get number 1. So this is number 1. Number 1. Let's actually change that. Let's make it 1 like that. So then the question is, which way is number 2? And so you want to number in the direction around the cyclic alkane that gets you to the next substituent the fastest. In other words, you'll have the smallest set, of numbering of possible numbers for substituents when you're done numbering. And so that means get to the next substituent the fastest, and that's the methyl group. So that's 2, 3, 4, 5. And so we have a 5-ol here. We have a 2-methyl, and then let's sort out what's over there at 5. It's got 1, 2, 3 carbons as the longest chain. So if I can do that correctly today, that's a propyl group. And that's, so it's a 5-propyl, but this is a complex substituent. So we have to deal with the other substituent that's on that propyl group. And it looks like there's a methyl group on the propyl group. And remember, we would count that one as 1', 2', 3', numbering the substituent itself so that we have a 2-methyl propyl, and that all of this is at the 5th position. And so when it comes to alphabetizing, we'll alphabetize methyl first and then methyl propyl. While we're at it, let's sort out some stereochemistry, since that's something we're going to have to do. On this side, I've got a hydrogen that comes out here, and on this side, I've got a hydrogen that goes in there. So let's assign the priorities for the methyl group. It looks to me like priority number 1 is going to be the carbon that has the alcohol attached to it. They're all carbons, so they're all going to be tied. It's a carbon here, it's a carbon here, and it's a carbon here. So then I'm going to look further down the chain, and the oxygen of the alcohol will beat that tie. The priority here for the methyl group will be priority number 3, because it's got 3 hydrogens. The next carbon over in the chain will be priority number 2, because it's connected to yet another carbon. And so it looks like it's 1, 2, 3 in this direction. This is an S arrow, but the lowest priority group is pointing towards me instead of away from me. So I should come up with R for that, you know. So I've got an R in that position. And so let's just absorb that for a second. I know that I like to mess up those configurations, but I think I got it right that time. All right, so let's come over here to this group and sort out this one. In this case, the low priority group is pointing in the correct direction. So we have to, we don't have to switch anything in this case. So let's think what I've got going on here. In all these cases, I've got a carbon, and a carbon, so I have to continue to look down the chain. So I'm going to look down the chain here. I'm going to look down the chain here, and I'm going to look down the chain here. So here are the 3 carbons that I have that are tied. Around the ring in the clockwise direction, that carbon is connected to, so it's this carbon, and this carbon that are all tied. And so around the ring in that clockwise direction, I have a carbon, I have a hydrogen, and a hydrogen. Over here, along the chain, I've got a carbon, a hydrogen, and a hydrogen. Around the ring in the clockwise direction, I have a carbon, a hydrogen, and a hydrogen. So it seems like even at this point, where I'm drawing the green circles, we're still technically tied. They're all CH2s. And so we have to continue to look out further to break the tie. And so that gives us another list of carbons. And now around the circle in the clockwise direction, I've got carbon, oxygen, and hydrogen. Around the circle in the counterclockwise direction, I've got carbon, hydrogen, hydrogen. And now along the chain, I've got carbon, carbon, hydrogen. And so now we've got a good list of atoms, and then that list of atoms can establish our priorities. And so this is priority number 1, this direction. The chain is priority number 2, and around the ring, it's priority number 3. And so I've got 1, 2, 3, with the lowest priority group pointing away from me. So if I look at that if I'm doing it correctly, that's an S arrow, and we'll leave it at S in that case. So now if I put it all together, what do we have? It's a cyclohexane parent group. And so let's see if we can attach all of the stereochemistry and all of the groups correctly. So it looks like I have a 2R, 5S, 2-methyl, 5, 2-methylpropyl, cyclo, I forgot something. What did I forget? Let's use the back button like it never happened. There's one other thing I forgot to do. Is that a chiral center? Yeah, I'm always forgetting something, right? Yeah, the alcohol's at a chiral center as well, so we should specify that chirality there. And so I think that one's going to be fairly straightforward. We won't have to do as much analysis as before. The priorities should be 1 for the oxygen on the alcohol, 3 for the CH2, and 2 for the carbon that's attached to 2 other carbons. 1 carbon there, 1 carbon there. This carbon's only connected to 1, so it's a lower priority. So I've got 1, 2, 3. That's the clockwise direction. So that's R. So I think I've got another bit of stereochemistry to include, and it's the R configuration. And so now if I put it together, I have 1R, 2R, 5s 2-methyl 5,2-methyl-propyl cyclohex N 1-all, and the 1-all is probably not needed, and it's probably not required, because it is understood that the alcohol would be at the 1 position. Certainly wouldn't count off if you were to not include it, or if you were to include it. All right, so I think we did that one right, and I think that one's worthy for YouTube because ultimately that's where it's going. And so there will be some alcohol nomenclature to deal with at the end of the day, but I think the only thing that's essentially completely new is that we're going to use the suffix OL. All right, and so let's get into alcohols. All right, so again, I'm not going to ask for alcohols that we go over the entire chapter. There are a few reactions and one mechanism that we have to deal with in order to sort out exactly what we wanted, in order to sort out all of the different. The question was, at the top you have 5-all. Yeah, I don't know why I have this 5 here. I don't know. So, sorry. Sorry if that led to some confusion. I think at the end of the day, we got the name right, though. Okay, so when it comes to alcohols, we've done some naming. In the full semester, in next semester, what we're going to do is we're going to talk about oxidation numbers. I know that in general chemistry, we've already done oxidation numbers, and I'll do a quick bit of it in organic chemistry. When it comes to the oxidation number of a particular carbon, in general chemistry, we learned a systematic set of hierarchical rules in order to assign oxidation numbers. In other words, one rule said oxygen always gets -2, and so we would just assign it that way. Hydrogen always got +1. We would just assign it that way. But there's actually a more straightforward way to assign oxidation numbers that actually doesn't involve any rules, and the way to do it looks familiar. An oxidation number of an atom equals the number of electrons it should have, and let me just say that's the number of valence electrons that it should have from the periodic table of elements minus the number of valence electrons assigned. And this is exactly the same way that we did something else. The oxidation number formula is exactly the same formula for formal charge. It's exactly the same thing. The only difference is, how do we assign the oxidation number? When we do formal charges, we assign the oxidation, we assign the electrons, we split them out evenly. And so if I were to think about something like this versus this structure, we can decide which one of these things is the better resonance structure by assigning the oxidation number for oxygen and for sulfur. For oxygen, it should have 6 from the periodic table. It has 1, 2, 3, 4, 5, 6. We're going to give the lone pairs all to oxygen, and we're going to split out the bond, 1 for sulfur, 1 for oxygen. So oxygen ends up having 7, and so the formal charge is -1. Sulfur should have 6 as well. It owns its lone pair, so that's 1, 2. Then we'll do 1, 2, 3 for the bond, so that's a total of 5. the formal charge is +1. On this side, it's 6 electrons assigned, and so the oxygen gets a formal charge of 0. Now, on the structure on the left, the sulfur is a row 3 atom, so it can do expanded octets. And so when I assign electrons for sulfur, it's 6 minus 1, 2, 3, 4, 5, 6. It has a 0 formal charge, as does the oxygens now, for the same reason. So we took one of the electrons over here on this one pair of electrons, and instead of using it as a lone pair on oxygen, we made a double bond with it and formed an expanded octet. So the formal chart, this is the better Lewis structure, because this resonance structure shows no formal charges versus this resonance structure, which shows 2 non-zero formal charges. So that's doing formal charges. We're assigning the electrons evenly, where we give one electron in a bond to one atom and the other electron in a bond to the other atom. And it doesn't matter how many bonds, whether it's a single bond, double bond, or triple bond. When it comes to oxidation numbers, the assignment of electrons is goes differently. With this, we assign based on electronegativity. And so if I were to think about the oxidation number of this carbon, then we want to assign the electrons differently. The calculation still involves 4 from the periodic table of elements because of its position there. Now we would assign the electrons differently. Well, it's attached to 2 carbons on either side, and so they have the same electronegativity, and so we'll assign the electrons in the bonds the same way we would in formal charges. We split them evenly. However, carbon is more electronegative than hydrogen, so both electrons in that bond get assigned to the carbon. When it comes to the oxygen is more electronegative than hydrogen, so it gets both sets of electrons assigned to it. Again, it's more electronegative than hydrogen, so it also gets both electrons in the oxygen-hydrogen bond assigned to it. And so if we were to think about the other hydrogens that are here, to fully flesh out the entire picture of the oxidation number of every atom, then in the bond to the each carbon-hydrogen bond would be assigned to carbon, because carbon is more electronegative than hydrogen, and this is the assignment of electrons that we would get. And so I've undid all of the bonds to assign oxidation numbers, because I want to make sure that I'm assigning the electrons correctly. And a picture helps at this point, because you have to get a little bit, you have to get used to it. Now let's then calculate the oxidation numbers. Well, for the carbon in the middle, it's 4 minus how many electrons we have assigned. 1, 2, 3, 4. So the oxidation number for the carbon in the middle is 0. You'll see that the rules that we learned in general chemistry still pan out. The oxidation number of the oxygen would be 6 minus how many we assigned. We assigned all 8, so that's -2. Take a look at all the hydrogens. The hydrogens should have 1. We assigned 0 to all of them, so it's a +1 oxidation number everywhere for every hydrogen. Now the final 2 carbons, what about those guys? The final 2 carbons have been assigned 1, 2, 3, 4, 5, 6, 7. And so it's 4 minus 7. The oxidation numbers of those carbons would be -3. -3. And so at the end of the day, the oxidation numbers Another rule that we learned in general chemistry is that the sum of the oxidation numbers adds up to the charge of the molecule. We'll see that this holds true as well, because we have 1 for each hydrogen, and we've got 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8 hydrogen. So that's 1 times 8. That's plus 8 from the hydrogens. We've got 2 carbons at minus 3. That's 2 times minus 3. That's minus 6. We've got 1 carbon at 0. So that's 0. And it looks like we've got 1 oxygen at minus 2. So that's minus 2. This all adds up to 0. Of course, the molecule is neutral. It's an alcohol. And so you would apply this to double bonds as well as triple bonds. If I had a situation like this, then I would assign the atoms or the electrons for each carbon the same way. All I'm going to do is focus on the central carbon, since the CH3s would be exactly the same. I would assign the oxygen all 4 of the electrons in the bond and none of them to carbon. The oxidation number on the oxygen would again end up being minus 2, because we would assign all 8 to it. And so the rule for oxidation numbers from general chemistry is sort of fleshed out from this rule about how we assign oxidation numbers based on this formula that we learned earlier on when it came to formal charges. It's the same formula, it's just the assignment of the electrons are done a little differently for oxidation numbers. Okay, and so I want to just pause right there real quick and make sure that there are no questions.
Question for you. For the carbon, it's a 4 minus 7. Where did you get the 7 electrons?
Okay. 1, 2, 3, 4, 5, 6, 7.
Thank you.
Yep. That undo button is magical. All right. So there's just a couple of reactions that we want to learn in this section. Now, when it comes to the synthesis of alcohols, you already know a couple of reactions. You certainly know the reactions of alkenes, where we can do addition reactions with dilute H2SO4 to form Markovnikov alcohols. We know how to do the same reaction with hydroboration oxidation. Where we can form anti-Markovnikov alcohols. What else do we know? We know that an alcohol could theoretically be formed from a substitution reaction. But of course, this is going to be in competition with the elimination product. And in most cases, the elimination product will be favored. But there's a couple of different ways there's a couple of new ways that we want to learn on how to synthesize alcohols. We also want to talk about the reactions of alcohols. Aside from the Grignard reagent, the reactions of alcohols fall into 2 categories: oxidation and reduction. That's why we started out this conversation with a little talk about how to assign oxidation numbers. The next bit with oxidation and reduction is the first example of when you should really focus on the reagent and what the reagent does, whether it does oxidation or reduction. The reason is that we're going to introduce some reagents today that will be with you for the rest of your organic chemistry life. Those reagents are sodium dichromate, what comes from chromic acid, and that's an oxidizing agent. The reducing agents, sodium borohydride and lithium aluminum hydride. And so let's take a look at first how we would make alcohols through reduction. And then we'll take a look at how we can react alcohols through oxidation. So if I want to take a look at a carbon that will ultimately get reduced to form an alcohol, then that means that the carbon has to be more oxidized than an alcohol. And there's some examples of carbons that are more oxidized than a carbon that has an alcohol on it. Aldehydes, ketones, carboxylic acids, and esters. These carbons are all more highly oxidized than a carbon with an OH group. It has more bonds to oxygens. And so if I reduce the oxidation number, then I can form an alcohol. And at the end of the day, there's two reagents that we want to think about. There's sodium borohydride, and there's lithium, let's back it up, NaBH4, and lithium aluminum hydride, LiAlH4. Both of these are reducing agents. And we're going to learn about how what we're talking about right now is how they reduce carbons that have bonds to oxygen. But later on, we're going to still talk about how they reduce carbons that have bonds to other atoms. But at the end of the day, they're still going to be reducing agents. And so, yes, you can start to brute force memorize these reactions, but it's going to be much more efficient to think about the reagents, to think about what they do as far as whether they're reducing agents or oxidizing agents, because that's how they're going to behave from here on out. The only other thing to know about these two reagents is that this one is a little bit weaker. It will not reduce every one of these functional groups. This one is stronger. It will reduce all of the functional groups present. So let's take a look at how these reactions work. I have two options with aldehydes and ketones. I can use either one of these reducing agents. So with sodium borohydride, I do it in one step. With methanol solvent. And it reduces the product of the reagent down to an alcohol. So this is the first reaction to note. I cannot use sodium borohydride with either of the other two functional groups. They're not going to work out for me. Remember, this can be an R, where R is any sort of hydrogen or other carbon chain. So this works on both aldehydes and ketones. Now, I can do the same reaction in two steps with lithium aluminum hydride, but I end up having to do a second step where I use water. And this is an important part because I want you to know why I need this second step. I need the second step because of this reaction. Once I form an alcohol, in the presence of hydride, and these reagents are hydride delivery reagents. Hydrides themselves can react with alcohols to do this reaction where I form alkoxide ions, R O minus. So this is how I might form something like methoxide or ethoxide. I might react it with a reagent like sodium hydride. When it comes to lithium aluminum hydride, however, the mechanism is slightly different, but it has the same idea behind it. If I have an aldehyde or a ketone, and I have lithium aluminum hydride, remember that the aluminum would want to have 3 bonds, so it's negatively charged. The lithium is the counter ion. This is a hydride delivery machine. So most all the time, hydride acts as a base. Certainly when I showed you the reaction of an alcohol with sodium hydride, the lone pairs on the hydride are acting as a base to do a proton transfer. In this case, it's not acting as a base, it's acting as a nucleophile. And so why do I need this second step with water? Because once I've done the nucleophilic attack and I formed the alkoxide ion, I have to have something in another pot that will come along and reprotonate the alkoxide and form the alcohol that I'm interested in forming. So it's hydride acting with its lone pairs, but in this case, since it's doing a proton transfer, it's acting as a base. But in this case, it's doing nucleophilic attack, and so it's acting as a nucleophile. Nucleophilic attack. And so this is the mechanism by which the hydride reagents reduce something. And this is a mechanism by which hydride forms alkoxide ions. So they're similar reagents. The hydrides act in similar ways in the sense that we've got a negatively charged hydrogen that's reacting, or we have lone pairs on hydrogens that are reacting. In one case, it's acting as a base because it's doing a proton transfer. In the other case, it's acting as a nucleophile because it's doing nucleophilic attack. So when it comes to lithium aluminum hydride, you need this mechanism, and you'll see this mechanism repeat itself here in just a second, in order to accomplish the transformation, because it forms an intermediate alkoxide ion that is isolated and then reprotonated in a second step. Okay. Now, the mechanism would work exactly the same way with carboxylic acids and esters. I'm ultimately going to get the same product out of both of these reactions. This is not a carboxylic acid. Let's make it one. In this case, the side product is water, and in this case, the side product is methanol. Because these carbons are more highly oxidized, I'm going to need more of the reagent. So it is lithium aluminum hydride, but I need it in excess. I still need the second step of water. The mechanism being the same as you saw before. So this is how we can form alcohols through oxidation, or through reduction, excuse me. We can take a highly oxidized carbon and use a reducing agent to form a less oxidized carbon, namely an alcohol. What we're going to do now is talk about how I can use an alcohol in a reaction to form other functional groups. In other words, I want to go the other direction. I want to talk about how I can take an alcohol and how I can oxidize it. How can I oxidize it? So the oxidizing agent that you should kind of keep in mind, and you don't need to know the mechanism for this one, is sodium dichromate. It's in a combination of H2SO4 and water. And it will oxidize a carbon with an oxygen as far as it can. So let's take a look. In the first case, it's a secondary alcohol. The secondary alcohol can get one more bond to an oxygen to form a ketone. In the second case, it's a primary carbon. So the primary carbon can actually continue to oxidize past the aldehyde, which it will do, to form a carboxylic acid. However, if I have a tertiary alcohol and try to react it with sodium dichromate, get no reaction. Because that tertiary alcohol is already, the carbon that contains the tertiary alcohol is already as oxidized as it can be. It cannot form any additional bonds to carbon. So this is a strong oxidizing agent. And you will see that it's so strong that later on, I'll show you just a quick example. Later on, it's strong enough that with a benzene, as long as there's an alpha hydrogen, it will actually break the carbon-carbon bonds and fully oxidize the benzylic position. That's not a reaction that you have to know, but I'm giving you a preview that, in fact, it is a very strong oxidizing agent. Well, what about this situation? What about the situation where I have a primary alcohol, but I actually want to form an aldehyde? There is a reagent that is an oxidizing agent, but isn't quite as strong as sodium dichromate, and it's PCC, and it's CH2Cl2 is the solvent. So the reaction involves the reagent PCC with the solvent CH2Cl2. This is a weaker oxidizing agent, and it will oxidize the carbon only to the aldehyde in the case of a primary alcohol. It is still, however, strong enough to take a secondary alcohol and oxidize it to a ketone. That's certainly something you can do as well. There is another reagent that is interchangeable with PCC. It's called DMP. And it will oxidize to an aldehyde as well. Typically, I only show the PCC reagent, but I wanted you to be familiar with this one as well. I don't think you had that on the exam. The question was, didn't we have that on the exam? I don't think so. All right, so that's it actually. Those are the only new reactions of alcohols that I want you to know aside from the Grignard reaction. So really what we're thinking about are the reagents that we learned. We've learned some reducing agents. And we learned some oxidizing agents. The reducing agents that we learned were sodium borohydride, and we learned lithium aluminum hydride. This one was a little bit weaker. This one was stronger. We learned PCC or DMP for oxidizing agents, and we also learned about sodium dichromate. This one again was stronger, and this one was a little weaker. And so when you think about them in terms of what they do, whether they do oxidizing or reducing, it's a little bit more, it's going to be a little bit more efficient later on when you see another reaction that involves a functional group besides a carbon that's attached to an oxygen. The example that I gave you earlier is a perfect example of that. If I give you the sodium dichromate here, and you've gotten yourself stuck on memorizing one reaction at a time, you don't say to yourself, what's this reagent do? You have to say to yourself, what's the product of this reaction? Saying to yourself, what's this reagent do, I think is more efficient. If you say to yourself, this reagent is a strong oxidizing agent, then you can say, the next thing you can say is, oh, there's a benzylic position, and benzylic positions are highly reactive. You'll learn that more next semester, and you can oxidize that all the way to a carboxylic acid. All right, so let me pause for a beat real quick and see if there's any questions about those reactions. So we're getting towards the end of it here. We're about to wrap it all up. Okay. All right. This is it. This is the culmination of the class. And that's the reaction of using Grignard reagents. And the cool thing about Grignard reagents is they form carbon-carbon bonds. Okay, so first of all, what is a Grignard reagent? A Grignard reagent involves reacting an alkyl halide with magnesium metal and diethyl ether and you form the Grignard reagent with this mechanism. No, I'm not, or with this reaction. I'm not going to actually, you don't need to know the mechanism of the formation of the Grignard reagent. These things that I'm going to show you, these products, these are the Grignard reagents. You don't need to know this mechanism, but you will need to know the mechanism of how a Grignard reagent reacts. So what ends up happening is the magnesium ends up donating 2 electrons to the carbon, and the carbon itself becomes somewhat anionic. The magnesium inserts in between the carbon and the bromide. And so I'm showing you this particular version here to show you that the carbon does end up being somewhat anionic. It's really a resonance situation where there is some sharing of electrons between carbon and magnesium, but compared to magnesium, carbon is so electronegative that essentially we can call the carbon anionic, and in fact that's the way that it behaves when it comes to the chemistry that it does. Now this works with essentially any alkyl halide, but the next step of the reaction will involve an SN2 process, so SN2 considerations will apply for the next step of the reaction. In other words, nucleophiles that are sterically hindered are going to have a little bit harder time reacting than those that are not. So it's certainly no problem to do them with primary and secondary carbons, but you should make some consideration in trying to make Grignard reagents like this. Oh man. These are going to have a little bit, these are going to react a little slower and not be so synthetically useful. So now that you've made the Grignard reagent, what can you do with the Grignard reagent? So remember that a Grignard reagent is essentially an anionic carbon. And this is where carbonyl groups come in. Because if you remember from our very first discussions about carbonyl groups, we can show a resonance structure with a carbonyl group that indicates there's quite a bit of positive charge on the carbon. And so what does that mean? That means that in the presence of a highly negatively charged carbon, in other words, one that is very nucleophilic, then we can get this reaction where the nucleophilic carbon, in the same way as before, when it came to hydride and its lone pair of electrons, can attack that carbonyl group. In this case, it forms an alkoxide ion, but now it has an additional, oh, I need one more carbon to count them correctly. It has an additional carbon-carbon bond. So that's 1, 2, 3 carbons. Here is the 1, 2, 3 carbons that got attached. And the new carbon-carbon bond is there. When you see these reactions given in a textbook, this is what we'll show you. I'll show you a carbonyl group. I'll show you something like this, RMgBr in step 1, and then I'll show you step 2, water. And what you want to show me as the product is the formation of an alcohol with this R group attached to it. And so why do we need the second step with water? Well, it's the same reason as it was before. The alkoxide forms and is isolated, but we need to reprotonate it to form the final product, which is the alcohol. And so that's where the water comes in. And in fact, you can use any proton source you want. Water or H3O plus works just as well. It's whether or not the solution ends up basic or somewhat or mostly neutral at the end of the day. So that's it. That's the reagent. This is the mechanism. And at the bottom of the screen is the reaction. So it's particularly useful because it forms carbon-carbon bonds in the process of making alcohols, and it forms them from carbonyl groups. And you do know how to make carbonyl groups. Recall that you can make carbonyl groups from alkenes through oxidative cleavage. And you can also make carbonyl groups from alkynes through various different ways. So it just depends on which version. You can do Markovnikov and anti-Markovnikov enol formation, and remember that enols are tautomerize and they form carbonyl groups. So whether or not you get an aldehyde or ketone depends on which one of those you choose. There's a lot of other stuff in alcohol groups, and so I just want to I don't want to go over the other things that we're not going to go over, but I do want to make one point. And that's that alcohols themselves are incompatible with Grignard reagents. Because the Grignard reagent, while it can act as a nucleophile, if you think back to hydride, it can act as a nucleophile or a base. Well, so can Grignard. If you react Grignard with alcohol present, then you end up with a mess of products because the Grignard reagent can also act as a base as well as a nucleophile. And so what we're going to do is we're going to save this conversation for organic chemistry 2. But ultimately, you'll need some sort of protecting group in order to make that reaction feasible.